So the speaker is Jingzhou from Tsinghua University.
Thank you for introduction. Hello, everyone. I'm Jingzhou from Tsinghua University. I'm excited to present our work understanding and detecting SQL function bugs using simple boundary arguments to triggering hundreds of DBMS bugs. First, let me introduce the background about SQL function and SQL function bugs. SQL functions are the core components in database management systems. They are used for querying, aggregation, and data transformation. However, bugs in SQL functions can be critical, leading to crashes, memory leaks, or corruption. For example, in ClickHouse, it supports built-in SQL functions to convert decimal to formatted string. However, a simple misuse of the two-decimal string with a star symbol as an argument can lead to a non-pointer reference and crash the whole ClickHouse database server. It shows the impact of SQL function bugs. However, SQL functions are quite different from the functions in programming languages. Here is an example of the XML updating operations. On the left, we have a SQL function called useUpdate XML in MySQL. This one-line SQL statement updates the first C tag inside A tag with a new structure that includes a B tag. The data types of the argument values and the return values of this function are all the string type, and its call sequence is very simple. It's only one statement. Instead, for library functions in programming language, it usually contains multiple predefined data types like here dog tag, not serializer, and its call sequence could be complex due to the dependency between function calls and variables. So, general-purpose library functions tested by tools such as AppleSuit, Rendup, they focus on generating valid function call sequence between different functions to satisfy their dependencies. However, SQL functions do not fit in these models since they do not have so complex call sequence. Instead, they have complex formats for different arguments. Similarly, DBMS testing works like SQLsmith or Squirrel. They focus on constructing syntactical correct SQL statements. However, for the generation for function expressions, they usually only support a small set of SQL functions and just generate by random. And this leads us to the central question: what kinds of SQL inputs are more likely to trigger bugs in SQL functions, and how to construct an effective way to test SQL functions? So to answer that, we conducted a comprehensive study. We collected 318 real-world SQL function bug reports from 3 popular DBMSs, MySQL, MariaDB, and PostgreSQL. These bugs are collected from their bug trackers with specific search keywords. Our methodology involves deep analysis of these reports, including their characteristics and root causes. Here are some general findings from our study. First, for the occurrence stage of the SQL function bugs, we analyzed the backtrace information available in 230 bug reports we collected. In usual, database process SQL statements in 3 stages, including parser, optimizer, and executor. As shown in the figure, 70% of them occurred in the execution stage. They crashed at the implementation of those SQL functions, not the parser or optimizer of the database. And for the function types of the bug-inducing SQL functions, 40% of them were caused by string and aggregate functions. Other types of functions like math, condition, system, JSON, date functions also appear with high frequency. And we also want to know how complex SQL function expressions are in these bug-inducing SQL statements. We found that most SQL queries that triggered bugs had less than 2 function expressions. It is showing that these bugs can be triggered with very simple inputs. Then we analyzed the root causes of these SQL function bugs. We reviewed each bug report to analyze the root causes and found about 87% are caused by improper handling of boundary values of arguments. They can be catalyzed into three groups boundary literal values and boundary result of typecastings and boundary result of nested functions. We find that about 30% bugs are caused by boundary literal values as arguments. These values are specified as constants or literals, and some SQL function mishandle certain boundary values from arguments. For example, in the regex matching of PostgreSQL, it mishandles the value near the maximum of int types and causes integer overflow. And in the format function of MariaDB, its buffer size for storing the result is too small and causing heap buffer overflow. We found that about 23% bugs are caused by the boundary results of typecasting. Typecasting involves certain converting a value from one data type to another data type in SQL. Sometimes function arguments are incorrectly converted the internal data types of databases and leading to SQL function bugs. For example, the MariaDB incorrectly calculates the length of the result string when converting, and it leads to a heap buffer overflow. And then we find about 35% bugs are caused by the boundary results of nested functions. These nested functions can construct boundary arguments with specific data types and values, such as special binary streams or extremely long strings in specific formats. For example, PostgreSQL triggers a stack overflow when handling a very long JSON string, and MariaDB triggers a segmentation fault by illegal comparison operations during processing the interval function, since the row data type they do not support the comparison. We also found some other root causes of SQL function bugs, including specific database configurations, specific table definitions, and complex syntax structures. So, based on these analyses, we proposed 10 boundary value generation patterns to generate function expressions for triggering more SQL function bugs. They include 4 patterns for boundary literals, and 3 patterns for boundary typecastings, and 3 patterns for boundary nested functions. For the patterns of boundary literal values, our pattern 1.1 generates the boundary values of some common literal data types in SQL, and pattern 1.2 is to utilize them as function arguments. Furthermore, certain functions may require arguments with specific formats of strings. These potential boundary values for such arguments can be roughly constructed by appending repeated characters via pattern 1.3 and 1.4. The table shows the values generated by pattern 1.3 and 1.4. It can be used to generate different types of values like JSON, IP address, regex. For the pattern of boundary typecastings, pattern 2.1 represents the implicit typecasting in database by the cast grammar. Pattern 2.2 uses the select Liang select subquery to construct implicit typecasting. It is because the row values in a same column of select statement should always be the same data type, so database will convert the value implicitly. Pattern 2.3 directly passes the arguments of one function expression to another function to create implicit typecasting. This is because arguments for different functions may follow different formats and data types. So passing the arguments of other functions can make the formats and data types mismatch and resulting implicit typecasting. And finally, for the patterns of nested functions, The pattern 3.1 is used to construct arguments of extreme lengths by repeating a prefix of the original argument via the repeat function in SQL. And pattern 3.2 and 3.3 employs other existing function expressions as the function arguments. It can construct potential boundary values or typecastings from other functions' return values. And then, guided by the boundary value generation patterns of the SQL function box, we designed a tool, Soft, that generates SQL statements based on these boundary argument patterns. First, Soft will collect rich function expressions from the unit test cases of databases. Second, it generates new function expressions based on our 10 patterns. Third, it generates SQL statements with these new it executes SQL statements with these new function expressions and identifies SQL function bugs if the database crashes after execution. We use Soft to test 7 databases, including PostgreSQL, MySQL, MariaDB, and others. Soft successfully discovered 132 vulnerabilities in total in 2 weeks. All of them are confirmed by the developers, and 97 of them have been fixed. These tables presents the detail of the found bugs. For example, Soft detects 16 and 24 SQL function bugs in MySQL and MariaDB, respectively. And among the 132 bugs, we find that the non-pointer dereference and segmentation violation is the most common. And the 3 types of our boundary value generation patterns, they detected 56, 28, and 48 bugs, respectively. Here are 3 bug examples detected by Soft. The first one is caused by a very long float value literals in the MySQL's aggregate function. It triggers a buffer overflow when MySQL processing this function. And the second one is caused by an incorrect implicit typecastings of PostgreSQL. During the PostgreSQL handling the JSON object aggregation function, the string literal are wrongly converted to the text data type and resulting in a heap buffer overflow. The third one is caused by the long JSON string constructed by the nested repeat function. It exists the buffer size for storing the string during processing the JSON length functions and causing global buffer overflow. They demonstrate the effectiveness of boundary value generation patterns and the bug detection of our tool Soft. So to summarize, in this work, we analyzed 318 SQL function bugs to understand their characteristics and root causes. And we found that about 87% are caused by improper handling of boundary values of arguments. And we summarized 10 boundary value generation patterns for the SQL function bugs. And we implemented Soft to detect SQL function bugs using these patterns and found 132 real-world bugs. And that's all. Thank you.